All right, so this is question 3 and 4, so spring 23. I said a student had asked about this. And good indicators what you'll see on the exam. Here first, what is the charge on the 4 microfarad capacitor? That's on this capacitor right here. The first thing that you want to do is to find the equivalent of the smallest part that's either series or parallel. So that would be these two. I like to redraw the circuit. So I have a 3 microfarad. That one, when they're in parallel, you just add them up. So that's 6 microfarads, 3 microfarads, and then I have 12 volts. And then I can find the equivalent of that, which is going to be 1 over 3 plus 1 over 6. That's equal to 2. So this is 2 microfarads, 12 volts. Then I can step back and ask myself, what is the charge on that equivalent capacitor? Q equals CV. So that's going to be C2 times 12, or 24 microcoulombs. That means that I'm going to also have that charge here, 24 microcoulombs, and here, 24 microcoulombs. That's our first rule for caps and series. They have the same charge. Caps and series have the same charge. And they have the same charge as the equivalent capacitor. So whatever I have on the equivalent capacitor, I also have on those individual capacitors. Then I can find the voltage. My voltage is equal to Q divided by C. That's 24 over 3, or 8 volts, and 24 over 6, or 4 volts. Notice that the 8 plus 4 add up to equal to 12. 8 is equal to 12. And then also notice that the 3 microfarad, which is the smallest of the capacitors, has the bigger voltage. Capacitance and voltage are inversely related. If C goes up, V goes down, and vice versa. If C goes down, V goes up. Inverse relationship between those two, given that they have the same charge. Also, recognize that the capacitors are different by a factor of 2, and so are the voltages. They're linearly, inversely related to one another. Okay, so the answer there, the charge on the 4 microfarad capacitor, oh, I didn't finish. Actually, let me finish. So I have 4 volts on that 6 microfarad. That means I have 4 volts here and here, because capacitors in parallel have the same voltage, and they have the same voltage as their equivalent capacitor. So I have 4 volts and 4 volts there. And if I want to know the charge on the 4 microfarad capacitor, well, Q is equal to CV. So that means that Q on this capacitor is 4 times 4, or 16 microcoulombs. That's on this capacitor right here. Definitely going to see a question like that. In fact, you'll see questions like that on every exam, and that's going to be certainly true for your quiz. 5 capacitor circuits, right? 5 capacitor circuits, and then 2 questions that are about capacitor circuits, but are just, conceptual. But there will be 5 circuits. They may or may not have numbers. You notice some of those don't have numbers. I don't consider those conceptual questions. Those are just, problems without numbers. Like this one, for example. This one's missing a lot of numbers. I have these 3 capacitors, 2 of which are in parallel, and I give you the voltage across this one, and I want to know what is the voltage across the battery. This one's a little more difficult because you got to sort of work backwards, and sometimes students struggle with that. I find that it's easier just to draw the circuit. So this is a capacitance C, and this is a capacitance 2C, right? Because when they're in parallel, I just add them up. And I also know that the voltage across this equivalent capacitor is equal to 16, because that was the voltage across this capacitor and across this capacitor. Both of those had 16 volts. And so the equivalent also has 16 volts. Now, if this capacitor is twice this capacitor, let's think, what would the voltage be on this one? Well, small capacitors have big voltages. There needs to be a factor of 2 in between them. So know that this capacitor has 32 volts. So I have 32 volts here. And now, since these are in series, I just say 32 plus 16, that's 38, plus 40 plus 10, that's 48 volts. So B is the right answer there. Those are trickier, and they're not trickier. You just have to, you can't follow the the set way that we answer them usually in class, because you have to sort of work backwards. But all the same rules still apply. All right? So those were the questions that had submitted to me for those two. And those are great questions. I don't remember what's on the quiz, but I wouldn't be surprised if you saw one of those or both of those or something like them at least, which there is one on every quiz. You have particular questions? Good. Okay. Well, you'll definitely see a question like this. Okay. All right. There's one on every test where you have to find the resistivity and identify the wire. Your first step on this is to find the resistance. And the resistance is V over I. That's going to be 0.32 over 20. And 0.32 over 20, that's 0.016, 0.016. 0.016. So I have a resistance of 0.016 ohms. The other thing that's different in this problem, that's not in some of the others, is that I don't give you the area, instead I give you the radius. And that might have been the mistake that you made. Maybe not, we'll see. But the radius is that, so I want to find the area. That's pi r squared. So that's pi times 0.005, 0005, 3.14159 times 0.0005 squared. And so I get the area is equal to 7.85 times 10 to the -7 square meters. All right, so that's my area. Usually on these questions, I give you the area, but I didn't in this one. Just make sure you read it carefully. Do I give you the area or the radius? Then I want to find the resistivity. So R is equal to rho L over A. Rho then is R A over L. I just solved that equation for rho, multiplying both sides by A over L to get rid of that L over A on the right-hand side. Then I put in the values that I have, 0.016. L is 1 meter divided by 7.85 times 10 to the -7. And I get 20,000. Ooh. Oh, yes. Thank you, Trinity. You're right. Yeah, so the area should go in the top, 7.85 times 10 to the -7. And then this should be 0.016. So I get 4.9 times 10 to the -5. Yeah, I'm not seeing that there. Huh. Well, the 1 doesn't matter, right, because it's just 1. Man, I'm messing this all up, aren't I? All right, so it's 7.85 times the 0.016. That's what you're saying, right? Y'all are so smart. Pretty great on this quiz, right? Yeah, so I get 1.3 times 10 to the bunch. Yeah, so it's the 1.26. B was or silver was the right answer on this one. So R is 0.016. A is 7.85 times 10 to the -7 divided by 1. And I get 1.3 times 10 to the -8, which is silver. So B is the right answer. Okay? I'm not sure what mistake you made. Maybe it was one of the mistakes that I made. Probably, yeah. All right. Other particular questions? I'll just sort of thumb through. Let me remind you that you're going to have 3 questions from Chapter 3. One of them will be a question like number 10. I'm going to go back up to Spring 23, by the way. This is Spring 23. One of them will be something like this is an Ohm's law question, where this also you have to know the definition of current, but it'll be one like this. There's one on every exam. It'll be one like this, where you have to know things about voltmeters and ammeters, right? This is spring 23. By the way, your Ohm's law is going to be simpler than this. It'll just be V, I, what's R, or I, R, what's V. It'll be simple. I hope everybody gets it right. That's my intention. And then the other one is going to be like the one that we just did, the resistivity question, which obviously that's harder than it looks because two of us got it wrong, right? That's okay. Where are you going? We're gonna make it, right? We need to learn how to do well on these exams and assessments. It's important for your future. Spring 22, no. Like this resistors, no. Nothing like that. You won't see 12, not 13, not 18. No resistors in series and parallel. Only capacitor circuits. Okay? On spring 22? Yeah, let's see. Yeah, but even you're not going to see 11. See, 11's from chapter 3. It is from chapter 3, but we're not doing these things because I've already told you the questions from chapter 3. And that's not one of those questions. I know that it's a little complicated because we're on the end of chapter 2 and it doesn't fit perfectly into my little legend that I gave y'all, unfortunately. So I'm trying to be really clear. Capacitor circuits. You'll see circuits. And then there are a couple of questions that are conceptual, like capacitors in parallel have the same below. They have the same voltage, right? Our capacitors in series have the same charge. Those sort of questions, okay? And then actual more traditional circuits where I show you a diagram and I ask, what is the voltage of this or the charge on this? Or maybe I describe it and I say 3 capacitors are in series. What is their equivalent capacitance? You'll see questions like that on past exams. Okay? Other questions? I'm okay stopping, but I'm okay just going through and browsing, and y'all can just shout out if you see something. You want to do that? Y'all are here. Like number 4 here, for example, you could see something like that. This one should be pretty straightforward, I hope, by now, because I want to know the charge on this one. I have 12 volts here. I know the 3 and the 6 in series is equivalent to what? 2 volts, right? And so if I have, not 2 volts, 2 microfarads. So if I have a 2 microfarad with 12 volts across it, then the answer is 24. I have 24 here and 24 here. Let me just repeat that. I'm going to draw, if you didn't see that, let me draw the figure. This is 2 microfarads. This is 12 volts. I know I also have 12 volts there. And so the charge that's on that capacitor is 24 microcoulombs. That's also on that capacitor and on that capacitor, because capacitors in series have the same charge. Hear about this one. I have 2 capacitors. Let's try to think about this without doing the equivalent capacitance, because the equivalent of 2 and 4 is it's a decimal number. I'd rather not deal with decimals. But if I have 2 capacitors, one that is half that of the other, and the total voltage is 9, well, what are 2 numbers that add up equal to 9, where one is twice that of the other? Well, I don't have that many numbers that add up to 9, right? 8 and 1, 7, 6 and 3, right? 6 and 3 add up equal to 9. And so now I need to figure out which one gets 6 and which one gets 3. What does this one get? This one gets 6. The small capacitor gets the big voltage. So I have 6 volts here and 3 volts here. That means, so the answer then is 6 volts. Okay? I intend you to work most of these questions in that way. That if you're really familiar with circuits and halfway decent with numbers, then you should be able to think through the answer without really going into a whole lot of, minutia with your calculator. For capacitors in series, yeah, the sum of the two voltages will always equal the voltage across the equivalent capacitor. And in this case, that's the voltage across the battery. But when we have a series circuit embedded within a larger circuit, it's the voltage across the equivalent. I see one like that. You're going to see one like number 6. Let's just double check we know this. Is the resistance of a voltmeter big? It is. Is the current through an ammeter small? Not necessarily. Is the current through a voltmeter small? Yes, very good. And ammeters, are they hooked up in parallel? No, they're hooked up in series. Let me just summarize those things. So for an ammeter and for a voltmeter, what we said was ammeters are hooked up in series, voltmeters are hooked up in parallel. Ammeters have a small resistor, and voltmeters have a big resistor. An ammeter is basically just a piece of wire. A voltmeter is a really big resistor, tens of thousands of ohms. And the ammeter has a very small voltage, and the voltmeter has a very small current. Always. Even if the voltage is really big, you're going to still have a small current. That's why the resistance is really big, right? If the resistance is a small current. If the resistance is small, I have a, well, if the resistance is small, I have a small voltage. Okay? These are the three ideas that I want you to know for each of the ammeters and voltmeters. And you'll see those questions. I mean, there are only 6 of those questions, right, for me to pick from. Remember, I am going back 6 years, not 5 years, despite what I told you earlier. You're not going to see this question with a graph. By the way, y'all heard that? Not that question. That is an Ohm's law question, but I don't give you that one. No power. This is a power question. There's no power. All right, no resistors, so none of this. There's some good ones. Like, for example, one of those conceptual questions could be something like this. There's another one that's capacitors in parallel. Oh, here we go. Everybody. All right. What was I saying? Oh, let's look at this one without the numbers. Those are often the hardest. So I have the 12 volts as C and 2C, C and 2C, right? Because these just add up, C plus C, and then I have 12 volts. And I want to know the voltage across C1. Small capacitor gets the big voltage, 8 volts. Big capacitor gets the small voltage, and so the voltage across C1 is 8 volts. Okay? I like those questions. I like these two where they have numbers. This would be 12 volts with 2 and 2 microfarads. And so the charge on C1, well, I know the voltage on C1, what's it? 6 volts. 6 volts there. So I have 6 volts here. Remember, capacitors in parallel share the same voltage. So I have 6 volts there and there. They all have 6 volts. And so the charge on C1 is 6 times 2, or 12 microcoulombs. Like this, make sure you can do that. You might have one like this where it's not an even number. Okay, so I know I told you that most of your circuits have even numbers, but this would just be 1 over 4 plus 1 over 4 plus 1 over 4, which is 1 over 3/4, which is 4/3. So knowing how to do fractions, that's not a complicated common denominator. I mean, they're all the same denominator, so it's already the same for you, so just beware of that. This is one of those. You want to measure current through a resistor. You should hook up the measuring device in what way? If you want to measure current, you hook it up how? Series or parallel? Measuring current. Series, right? Ammeters are in series, so it's in series with the resistor. Make sure. Y'all can't see that, can you? I will zoom in. I'm just looking for some particular things. I was looking for a good Ohm's law question. This is the last one, isn't it? Yeah, hold tight. Okay, let me just look up. Okay, here we go. Number 7 is one I'm looking at. This is spring 23, number 7. When I say Ohm's law is one, this is a good example of one where it's just Ohm's law. Your electric oven, apparently, V here is equal to 240 volts. I is 60 amps. And I want to know what is the resistance. R is V over I. So that's 240 over 60, which is equal to 4 ohms. Anytime you have a heating element, it's going to have a really small resistance. You want any sort of power. Oh no, not like a regular wall. No. That's a wall. Okay. All right. Y'all feel fairly comfortable with this? Let's get 100%. Huh? Okay. You can do that, right? But let's not make it this one. This one's going to be an easier one.